Hello, this is a video for compiler design, COMP442 and 6421. This is for week 5. There was 2 videos for week 5. First one was error recovery, top-down parsing. That kind of finished the description of what you need to do for the parsing. For the assignment number 2, the second part of the assignment number 2 is how you are going to generate an abstract syntax tree. Now, the way to do this is to use what is called syntax-directed translation, by which as you're doing a parse, as you're determining the validity of the syntax, as you're tracing a parse, you are eventually going to generate an abstract syntax tree as you are doing the parse using what is called syntax-directed translation. So that's what I'm going to explain the notion of syntax-directed translation, how it works, and how it, especially how it can be tricky if you had to remove the ambiguities and the left recursions in your grammar. Syntax-directed translation can be very simple if you'd be using a bottom-up approach, where essentially your parse tree is not kind of, I might say, complexified by having transformed your grammar, by having to remove the ambiguities and the left recursions. Repeat, if you are using a bottom-up parser, you don't have to remove ambiguities and left recursions. So your grammar stays pretty much simple. The effect of having to remove these, if you want to use a top-down parsing techniques, is then that your parse tree is going to become much more wide, as we saw and as we will see in this lecture. So the difficulty here is, especially if you're using top-down parsing for syntax-directed translation, is dealing with the aftermath of having changed your grammar. So let's go with that. Okay, so this is the introduction to what is syntax-directed translation. Here, I will explain the mechanism by which you can implement syntax-directed translation, which can then be used to do different kinds of translation. In our project, the translation we will do is we will essentially translate the sequence of tokens into an abstract syntax tree. So that's the translation we will apply. Of course, in general, or you might expect that translation means from one language to another. You can actually use syntax-directed translation to automatically, transform your sequence of tokens into executable code. You could do that. But in our project, what we will do, the translation we will do, is to transform the sequence of tokens into an abstract syntax tree. Then after you will have this tree for assignment 3, you will basically take this tree, you will traverse the tree to do further processing. So the translation we will be doing in the project is translating sequence of tokens into an abstract syntax tree using syntax-directed translation. So what is syntax-directed translation? So it's a translation process that is driven by the syntactical structure of the program, as is generated by the parser. So as the parser executes, it actually somehow is tracing or constructing, you might say, abstractly speaking, a parse tree. So it's by going over all the right-hand sides that it's going over as it's doing the derivation, it's actually forming some kind of tree that follows the occurrence of the uses of each of the right-hand sides that it chose to use. So it's somehow constructing some kind of parse tree. As we saw earlier, there is a difference between a parse tree and an abstract syntax tree. The parse tree includes all the symbols, which are not necessarily useful to do the further processing. For example, when you do the code generation, you don't need in the way some nodes that are open, close parenthesis, or star, the operators and so on. You don't need them. Okay. So what you want is to have an abstract syntax tree and not the parse tree. So that's one thing that sometimes I always have a few students in the project that they eventually generate a tree. Yes, they generate a tree data structure, but they actually generate a parse tree. That's going to lead to many problems down the line when you want to do the processing after. So you should really make sure that you generate an abstract syntax tree and not a parse tree. Of course, building a parse tree would be much easier than building an abstract syntax tree, as we will see. But yes, it's easier, but it's going to lead you to many more problems down the line. Okay. And then this abstract syntax tree should be generated as you're doing the parse. So every step of the way, you're constructing nodes, and then you're grafting nodes to parent nodes and so on until you have the entire tree of the entire program that is represented as a data structure, a tree data structure. Today, I'm just going to explain what is the concept of syntax-directed translation. In a further videos, we will see how to construct a tree out of that procedure, using that procedure. So there is two different, I'm going to show some concepts here before we go to the actual procedure. There's this notion of analysis and synthesis, because here what you're doing is you want to do some translation. As I explained before in the beginning of this course, if you want to translate something, you must first understand what's the meaning of it, which as you're trying to determine the meaning of something, you might realize that it cannot have a meaning. So something might be syntactically valid, but it can actually potentially have no meaning. So you need to do the analysis of this thing, then you can actually hope to translate it. So there's going to be some checks that you're going to have to make along the way. Check, for example, to check if you can actually be it's possible to actually generate an abstract syntax tree out of the program that you have, or if there might be some errors and things like this, because that can also happen. So all this to say that as you are doing this procedure, there is some checks that you have to make very often, especially when you come to graft. So you have found some subtrees and then you want to graft these subtrees into a higher level node. There has to be sometimes some conditions for these to be valid children of this node here before you do the graft, or else there might be an error. That's what would be the analysis part. So there might be syntactic analysis. Of course, as you're doing the parse, you're doing syntax analysis. There might also be semantic analysis that is involved. Eventually, in assignment 3, we're going to do the semantic analysis. Point is that there's going to be, there's going to be some checks that are going to be made to enable the creation of the tree. But eventually, later on, we're going to add some checks inside somehow of the processing of the tree to trigger some methods that are going to do semantic checking. But that's going to be done after the AST has been generated. Though there are some semantic checking that you can actually do as you're generating the tree, as we will see. And then synthesis is actually the another word to say that you're translating, you're representing something into a different form. Okay. So that's where you're translating this thing that you found that is syntactically correct in another form. In our case, we're going to translate this syntactically valid program into an abstract syntax tree. in all compilers, you also have optimization stages that result after. In this course, we don't cover optimization. Not to say that it's not important, but there's more than enough to cover in this course without optimization. It's actually a very important of compiler design optimization, but it's also extremely technical. Okay, so the in this distinction between analysis and synthesis, here basically when you do analysis, there's essentially some conditions that you're trying to see. These conditions are there, and if the conditions are there, then you can actually translate. If the condition is not there, then you have found an error. So essentially your analysis becomes some kind of transition between the processing of the grammar and the actual translation. So if the grammar, as you're constructing the parse, you find some errors, then you may be realizing that there's no point in actually making the translation. That's kind of error that we'll see later when you do semantic analysis. Now, when you do syntax-directed translation, this actually induces a lot of coupling between the syntax analysis phase, or the parsing, and the semantic checking phase. So you have to do some kind of semantic analysis as you're doing the translation, because some of the translation is dependent on some rules, semantic rules, to be valid before you do the translation. So the more you actually doing a lot of checking as you're doing this syntax-directed translation, the more you're actually bunching everything together in your compiler, and you're potentially introducing all your semantic checking at the same time as the parser is running, and potentially even your code generation as the parser is running and its semantic checking is being done and the code generation is being done. Okay. You can do that. That's actually how I used to have it in this course. But a lot of students got very confused, because, especially in the programming, because it starts involving a lot of different things in the same procedure, the parsing procedure, and that becomes extremely confusing, especially if it starts going wrong. It's possible that the things you add for the later stages are going to get confused with the things that were already working, and it's going to make things that were already working to stop working. And then from there, it becomes just a nightmare. That's what the problem is with high coupling. So if the way to solve this problem is to actually as you're doing the parse, you generate an intermediate representation, such as the AST, and then your further steps are actually taking the AST and then processing this AST, so that the parsing is somehow decoupled from the semantic analysis and the code generation. You can even separate semantic analysis from code generation after, as we will see much later. Okay, so yes, you can use syntax-directed translation to bunch everything together, the whole translation process as the parsing is being done. It's not a good idea, generally speaking. It's not impossible, but it's likely to create problems, and also likely to make it less possible to actually have a parser which can be retargetable to, for example, generate code for a different computer. Now, what you need to have introduced in your parse, because now we saw how to do the parsing. Now, basically what I'm saying is that you need to, as you do the parsing, you need to create a tree. Of course, that will involve some methods that are going to create nodes, and potentially going to graft nodes to create subtrees and so on. So these are methods that are going to have to be called. So in abstractly speaking, these are called semantic actions. These are actions that are there to either make a semantic check or to implement a semantic, to translate a part of the syntax into another semantic meaning. That's what our semantic actions. They are an abstract representation of the methods you're going to call that are, in our case, going to generate the abstract syntax tree. So you create semantic actions and you somehow inject them into the parsing process. So depending on what right-hand side you're currently executing, then you're going to introduce some semantic actions. For example, if you are currently parsing a variable declaration, then you're going to introduce some actions that are going to aggregate the information about what's the nature of this variable that is being declared. So for example, if you have int x, well, that's in, of course, in another language, but 2, 3, then essentially this is a variable declaration for a variable named x that is of type int, and that is also of an array of 2 by 3. So eventually you're going to have, and eventually also important to realize that as you are doing this parse here, this is actually creating quite a large tree here. So what's the job here is that as a result of parsing this entire subtree that represents this variable declaration, you want to have it so that to have a mechanism that makes it so that when you come back to the top of the tree after generating or traversing this tree, you want to come back on top of the tree and having gathered somewhere the entirety of all the information that there is to know about this subtree which defines X. Okay, so you're going to have to aggregate all this information in a single container somehow to define what is all the aspects of X. Okay, so that's what is examples of semantic actions that are aggregating information. Okay. So semantic actions are functions whose goal to accumulate and or process semantic information about the program as the parsing is done. So you can imagine that as you're processing the subtree that represents this variable declaration at different places in this subtree, at different nodes of the subtree, you will eventually call some semantic actions that will aggregate a part of this information as the tree is being traversed. As the tree is being traversed, abstractly speaking, by the parser. So you're going to need to inject in somehow in the right-hand sides that are being parsed some semantic actions that are going to gather a little bit of this information and put it into this container. That's just an example for particularly a variable declaration. Different pieces of information are gathered during the parsing of different syntactical structures. So that's an example for a variable declaration. You would have a totally different example and different semantic actions that would be involved if you have a function header. Function header has many more things into a function header. So you would have different semantic actions that would be involved in the processing, the accumulating of information for a function header. Same thing for an entire class or for a function definition. So you have to define what are all the semantic actions that you need to inject inside of your right-hand side so that they all synchronize together to all work, I would say, in harmony with one another to actually gather all their little bit of information correctly so that they feed the information to their parent nodes and so on, so that when you come at the end, that at the top of the tree, you have all the information correctly organized and processed by these semantic actions that you have inserted inside of your right-hand side at the right places. So these pieces of information are named semantic values. For example, the fact that X, that this ID here, this ID X here is actually the name of this variable. It's one piece of information. This int here is actually the type of this variable, another piece of information. This 2 and this 3 here are two dimensions that determine what is the size or the dimension of the array that X is, in fact. So X, int 2, 3 are all semantic values or semantic attributes that are gathered, accumulated into a semantic record. So the semantic record is actually the container. In this case, it's a container that contains an aggregation of semantic values. And these semantic records are created by semantic actions. Some semantic actions will even process some of the semantic records, or use some of the information in semantic records to do some further processing. For example, doing some checking or doing further aggregation. A problem. Some of the information that must be gathered span over the application of several syntactical rules. So if you look into your grammar and look into all the different rules that are involved in processing a variable declaration, there's quite a number of rules here, number of right-hand sides and non-terminal symbols that are involved in processing this very simple thing here. So it would be kind of simple if all of this here could be parsed using a single right-hand side. But because it is not, because it is essentially parsed by using a combination of several right-hand sides, then it becomes much more complicated. You must have then coordination between processing of each of these right-hand sides that create their own subtree and so on, so that it all works correctly together. We will see that you have, if you want it to work correctly, then you have to proceed in a very mechanical manner. Okay? You can't just improvise here. It has to be a very mechanical way of actually organizing everything. So this eventually, because you use different right-hand sides, each right-hand side represents a subtree, and then you eventually have different subtrees of a bigger tree. So then what's happening is that the information must be migrated across the nodes of this tree, across different levels of the nodes of the different levels of subtrees inside of a tree. So you must have attribute migration. So these attributes here, they must go up in the tree so that they appear at the top of the tree, even though the information was gathered much lower in the tree. So information must go up in the tree. So that's what is called attribute migration. So the information, yes, is gathered at the leaves of the tree, but then sometimes the tree has many levels. So the information must go up in the tree so that it appears at the top, where you have, at the top, you have the entire information gathered into a single semantic record. So it is simple when the tree, we will see that that attribute migration is actually what makes it difficult, especially when you have messed up with your rules by, for example, removing left recursion and ambiguities. Attribute migration can be simple, can become very complex. So in the project, we aim to accumulate information about syntactical constructs and represent them as subtrees. So we want to build an abstract syntax tree. So when we see a certain syntactical construct, such as this here, eventually the semantic records we're going to build is going to be a subtree. So essentially, we're going to want to translate that into a node that is actually connected to a children node that are themselves connected to children. So basically, that the result of processing this is going to be a subtree that represents this variable declaration. That is what's going to be our semantic records that we produce as a result of syntactic directed translation in our case. So you're going to have a different subtree for different form of subtree for variable declaration, function declaration, class declaration, statements, expressions, and so on. That we will see in next week, in the second video of next week. So how does this, so this was here describing things in a more abstract way using concepts. In terms of implementation, these semantic actions that you have that are generating these or aggregating this semantic information are going to be implemented as semantic routines. So you're using an object-oriented programming language, it's going to be semantic processing methods that are going to do the semantic analysis by performing semantic aggregation and or semantic checking. So semantic aggregation is when you aggregate information together, for example, to create a semantic record like this, or that at the leaves of the tree you have two atomic semantic information that are nodes that you are going to graft into a parent node that represents a more complex kind of syntactical construct. So you're going to have methods that are going to create nodes, some other methods that are going to graft nodes that were already created to create a subtree, and so on and so forth. That's how it's going to go. So let's say, for example, you have this statement here, A is equal to B plus C. So eventually what you want to have, here it looks simple because our grammar, here I'm assuming that the grammar has not been transformed by removing left recursions and so on. So assuming we have a grammar of the form E, E gives E plus E, okay, that has not been transformed. So in this case here, just to show that it's can be simple. So here you have, for example, let's say you want to determine what is the type of this entire thing. So first you must determine what is the type of A, and then the type of B, and then the type of C. So then you have the type of each of the constituents. Then as you come here at this level here, if you want to determine what is the type of B plus C, then you must have some kind of semantic checking rule that will check if it's the type of B and C are valid types for arguments of the plus operation. If it is, then this rule will tell you what's the resulting type, and that will tell you what is the type of B plus C. So you see that you would have to have a semantic checking rule that is going to determine what is the type of B plus C. Then that will have to be checked also against what is the type of A and the type of B plus C to determine if you can actually assign the value of B plus C, which is of a certain type, into the value, into the container A, which is assumed to be of a certain, declared of a certain type. So basically the type of B plus C must be the same type as the type of A. Then you can, once you have the type of B plus C, you can compare it with the type of A. If it's the same type, then that becomes the type of A is equal to B plus C. That's the kind of thing that needs to happen. So you see that you have some rules that need to be here that are going to do some semantic checking. And once the semantic checking passes, then it will infer some new aggregated information. For example, the type of B plus C or the type of A is equal to B plus C. So semantic actions assemble information in order to validate and eventually generate a meaning or a translation for the program elements generated by the productions. Okay. So you're going to insert inside of your right-hand sides literally rules or function calls that are going to make these actions that are there to validate information, propagate information, aggregate information. So these are the starting point of the translation. eventually, when you want to do translation, you're going to have other rules, semantic routines that you're going to add that are going to do the translation. Of course, the translation is one of the main things that Compiler is doing, so that's a very important part of it. Now, how is this going to translate into either recursive-descent predictive parser or table-driven predictive parser? So here I'm explaining how does this correspond, how does these actions and so on map into, because you have basically here you have a parse tree. Okay? Your parser is going over a parse tree as it's operating. Now, how does this semantic action map with the leaves of the tree and then the intermediate nodes in the tree and so on? So first you have semantic actions at the leaves of the tree. So of course, at the leaves of the tree, what you will do is to gather information. Normally you will gather information either in the token itself. For example, if you see an ID, then you will get the name of this ID from the token. Another thing you may do, if you're further down the road in the processing, you can actually, for example, if you see an ID X as in the node of the tree, then you can actually, yes, know that it's X, but then you can actually check if you have a symbol table, what is the type of X. Okay, so if you already have the symbol table, then you can make checks like this. Okay, but in our case, symbol table is going to be built later on, so we will not do this. But if you would be the full translation of syntax directed translation, you would have to do things like this. So you come at the leaves of the tree. This is where you start gathering the essence of the atomic elements of your information that you are synthesizing. And then in the intermediate nodes, this is where you will start aggregating information. So you have two leaves, and then you figure out that these two leaves actually have a parent node, and the parent node is actually representing a certain non-terminal symbol that you are parsing using a certain right-hand side. Then this right-hand side is going to somehow traverse this node, and it's going to come back at the level here, in which case it's going to be able to get information from these two nodes and potentially aggregate this information so that this parent node here has the aggregated information that it can then pass to to its parents itself. So the intermediate nodes are going to be there to aggregate information or validate that the combination of information that it got from its children is correct, and then do some further aggregation and processing, and then present this aggregated information to their parent nodes. So parse trees are also related to grammar rules, as I just said, but also to semantic actions. So for every of the left-hand sides or syntactical constructs that these left-hand sides represent, then you will have some semantic actions that are going to be associated with them. Okay. Even this might be different semantic actions that are associated with different right-hand sides that are defining this left-hand side or syntactical construct. Because, for example, you could have a statement. So if you're parsing a statement, well, it's going to be very different if you're parsing an if statement, which is generating a very specific kind of tree, which requires very specific aggregation and checking and so on. Very different from it is a while loop or a return statement. Depending on which branch you take, you're going to have different operations, semantic operations to be done to process this different flavors of what can be a statement. Okay, so how do you insert these right-hand side, semantic actions in the right-hand sides of the grammar? Because that's what you're doing. You find a right-hand side, and then you insert at different places in the right-hand side some function calls that are doing some processing. Either aggregating, either getting information from, for example, the token, or passing information to the next symbol in the sequence, so that they can continue aggregating information as you go in the sequence. So if you're using a recursive-descent predictive parser, then essentially what you have, because these semantic actions are literally function calls. Okay? So you're going to have to introduce function. If you're using a recursive-descent predictive parser, you're going to introduce function calls to these semantic to functions that are actually implementing semantic actions. And then the attribute migration is going to be performed using parameters that are passed and returned between the parsing functions. So these semantic actions are going to be processing some semantic information. So you need to pass to them the semantic information so that they can process it, or actually return it so that it can be processed further down the line. Okay, so it's going to be done using parameter passing and returning values from these semantic routines or function calls to semantic actions. So that's the that's generally how it's done for a recursive-descent predictive parser. I'm going to explain here, and I'm going to show that there's an alternative way that you can use if you prefer so. For a table-driven predictive parser, semantic action symbols are inserted in the right-hand side. So in the execution of the table-driven predictive parser, essentially when you peek in a table, in the table, you essentially have a right-hand side, which you will then push onto the parsing stack. Okay. And what you do is actually you will introduce in your right-hand sides other symbols, which are semantic action symbols. You will insert them inside of your right-hand sides, and they will actually be pushed upon the stack. And then when the parser will execute, if it sees one of these symbols upon the stack, and it's going to map this symbol with a certain function to be called that's going to trigger a certain action, semantic action. Very often, and that's what you're going to have to do, these semantic actions are going to have to use their own semantic stack. Semantic stack is going to be there to accumulate some information as the processing is being done. Okay. So you're going to end up having the parsing stack, and then the semantic actions that you will encounter on the parsing stack, they are eventually going to process things, accumulate information, and then push it onto the semantic stack. And then some other actions will actually take records from the semantic stack, do some processing, and then push another record as a result. Alternatively, you can actually have the recursive-descent predictive parser that is using the same kind of stack mechanism as semantic stack. Okay. So that's an alternative way. But I would say that it seems like attractive, but it introduced the other difficulty, because we all know that when you use a stack to accumulate information that is consumed and produced by different methods, then if one of these methods is doing one more or less push than it should, or pull or push or pull that it should, then the stack goes out of synchronization, and everything goes to hell. Okay. So I'll just say, yes, this is a possibility, but that introduces this additional potential problem. Not that this problem is not there if you're using this here. If you're using this method here, by using parameters. If you don't pass the right number of parameters and so on and so forth, and of course, it's going to have the same effect. Now, okay, so semantic routines and this notion of attribute migration and so on, it can actually be part of the made part of the grammar itself, so that you would deal with it, theoretically speaking, in the grammar itself, and that you would have like methods that would be there to actually automatically reason and represent them mathematically, and then process them using mathematical definitions. Okay. And then eventually be able to transform a grammar that actually includes these attributes that are now part of the grammar. So that would be named what's called an attribute grammar. So that's something that exists, but that's something that will not use in this course. Not to say that it's not useful, but this is an entire other subject which I chose to not go into in the course. So attribute grammars would augment additional context, ordinary context-free grammars with attributes that represent semantic properties, such as, for example, the type, the value, or the correctness of the constructs that are used in semantic analysis or semantic checking, and eventually code generation or translation. So it is possible to, there's some theories that exist that you can actually represent your semantic records inside of a mathematical model. And for example, if you want to transform your grammar that is represented as an attribute grammar, then there's some transfer mathematical definitions of how transformations can be applied and so on that exists. I'm not going to use this in the course. Okay. So close parenthesis on attribute grammars. Again, something very important in theory, but not going to use it in the course. Close parenthesis. It's also useful to keep semantic checking and semantic translation distinct. So semantic checking is actually making some checks to see if the program can be translated. Then after it's determined that it can be translated, then you can have the translation. Now, the thing is that depending on what you want to translate into, then you may have some different methods that are going to be called depending on what you want to translate it into. Now, if you combine these two things together, you make it more difficult later on if you want to translate into something else. You make it difficult to basically retarget your semantic translation. So if you want to have a retargetable compiler, you should separate these two domains, basically the semantic checking and the semantic translation domain, from each other as much as possible so that you can target a different translation to translate into a different data structure or language. We will see that eventually when we see how to do the actual semantic checking and translation. We are going to see how you can use actually a visitor pattern to make the separation between each of the different translation steps. Okay, so what are the attributes? So again, here, this is a definition of an abstract concept. So what is an attribute? An attribute is a property of a programming language construct, including a representation. For example, including either a representation, a data type, a symbol table, a value, a memory location or size of memory required, or translated code, and so on. So in our case, our attributes that we will generate are going to be representation, which is nodes in an abstract syntax tree, where some nodes can be leaves and some nodes can be intermediate nodes that represent a subtree. Okay. The example I will give here will more revolve on a notion of type, so that you are basically passing information about the type of the elements of an expression, and then you want to find the type of the entire expression out of the constituents of the type of the constituents of the expression. So implementation-wise, these attributes are actually semantic records. Okay, so what I was describing here, essentially a semantic record, that is some kind of tuple that contains all the bits of information that there is to know about this particular variable declaration. Process of computing and assigning the values of an attribute is called binding. Now, you may have seen binding. I'm sure you've seen that in programming language, especially when you in C++, you see that term very often, dynamic binding. So when you have, for example, polymorphism in C++ or any other language that's using polymorphism, object-oriented language, they say what you have is dynamic binding. The idea of binding is that you have a certain symbol and then you want to somehow bind it to a certain meaning. So example, you're calling a function f of a certain object. There might be this object belong to a certain class which has subclasses. These subclasses might each have a function f as well as a superclass. So which function are you talking about? Okay, so that would be in the case of dynamic binding if you have polymorphism. In our case, in this course, we will not have dynamic binding. When we will have to determine binding, it's always going to be possible to determine the binding at compile time, which is called static binding. Okay. So anytime we want to somehow associate a certain symbol with a certain meaning, we are always going to be able to do that at compile time. But these are things that we'll see much later in semantic checking and translation. But nevertheless, when you actually compute an attribute, then you have a certain concept and you want to assign a certain value to this concept. So that's actually binding. General concept. Now, what about attributes migration? So we saw what is attributes here. It's a property that you encounter as you are processing the elements, the syntactical elements of a program. Then these attributes actually need to be migrated up the tree, for example, in order to aggregate them so that they are become a part, a component, a part of the semantic description of an entire concept. Okay. For example, like here, this int here that you got from processing at a leaf of the node, it has to be actually be represented at the level of the parent node of this entire subtree, so that this int here is actually aggregated somewhere inside of this is present at the level of the parent node that represents the entire subtree. So you need to migrate this information int from the leaf where you found it up to the level of the node that is the parent node of the entire tree. So that's what is attribute migration. Moving from the bottom of the tree up following the parents is actually called synthesized attributes. So that's the most simple kind of attribute migration. But you also have what is called inherited attributes, the attributes that are gathered from a sibling. Okay. That may seem strange, but we will see a lot of examples here in this video and the following ones too. Now, okay, so here's an example of semantic rules. So these are operational semantic rules. Okay, that's another part of programming languages that I'm not going to cover here. How do you define mathematically the semantics of a programming language? Okay. This is one way that you can actually represent semantics of a programming language using what is called operational semantics. So how this works is essentially these are some kind of inference rules that what you have at the top of the line here is our conditions for this rule to actually apply. Okay. So for example, let's take this one here. So if I have, for example, I have this rule here, E is E plus E, or E1 is E2 plus E3. This is the rule, semantic rule that defines what is the meaning of a plus operation. So for this rule to apply, I must have that this E here represents a value of a certain type TAW. Then also, I must have, for this rule to apply, I must have the fact that this E3 here represents a value that is of type TAW. Now I see here that I have the same type here. So this rule says the type of the left and right operand of the plus must be the same. If it is, then the value and type of this E here, E1, its value is the addition of the value V2 and V3, which is the value of these two here. And the type of this value of E1 is the type TAW. So it's the same type as the two operands. Okay. So this is how you define operational semantics rules. This is another very big part of what is the reasoning of and the theory of programming languages, programming language semantics. That's as far as we're going to go in this direction here. Not to say it's not important, but we have, I want this course to be more practical rather than theoretical, though it covers a lot of theory, but we're not going to go in this aspect of the theory. So all this to say, you can represent the meaning of your rules or the semantic meaning of your rules into rules like this, of your semantic rules. You can associate with every semantic rule that you have, syntactical rule that you have, you can associate a semantic rule that gives the meaning of an expression of this form. Okay. So you see here that you have conditions. So these are your semantic checking that you have to do. Okay. And then here, this is actually giving the meaning. Okay. So this is the semantic checking part, and this is the translation part. So in this case, if you have, for example, y is equal to 3 times x plus z, then eventually you can use these rules here. So essentially here, this let's go back to this rule here, which is used at this point here. Okay. So essentially, this rule says here that this operand here must be of type TAW. This operand here must be of type TAW. They are of the same type. If they are, then the result value of this plus operation is to add this value with this value. So essentially here, that's what I did here. The value of E is the addition of the value of this expression here and the value of this expression here. And the type of this value is the same type as the two operands. Okay. So here, my information is aggregated as well as migrated as it's going upwards in the tree. Okay. And eventually, I end up having the entire information as to how to compute this value for, in this case, for example, 3 times x plus z is here, as well as the type of this expression here. And then here I have the entire meaning of the entire value of this whole statement or expression. So here, the only thing that you have is actually synthesized attributes. The information is migrating from the child to the parent always. Here you don't have the fact that some siblings are inheriting information. The information is flowing sideways in the tree. This would be inherited attributes. Here you only have synthesized attributes. Here, the aggregated semantic information is always available on the same subtree. So for example, for the times operation here, I have all the information I need to process this times information inside of this subtree here, which will be different as we see in the following example. So this is the case here, but using our grammar. So of course here, this grammar, you would have recognized that this is the non-transformed grammar somehow of what we used to have before we applied the transformation to remove the ambiguities and left recursions. So after we remove these things, I remind you, we have to remove them because they're not part of what is an LL1 grammar, which is necessary condition for doing a top-down predictive parser. We had to remove them, so that's what happened to our grammar. Now, what's happening here is that if you build a tree, for example, for A plus B times C, then you see that this times operation is actually computed at this level here of the T prime. So the thing is that as you want to process the times here, you have this C here, which is the value or the type of C, but the B is actually here, which is not on this subtree here. So the times operation is processed here, but it has only the right operand. It does not have the left operand on this subtree here, because we had to transform our grammar, and then it has basically took the right operand or the left operand and somehow factorized it and put it into another rule, okay, which is now creating the fact that our left operand is separated into a sibling of the T prime. Okay. Now, of course, what's going to need to happen is that T prime will need to have access to this information here and be passed this information from F to T prime, so that T prime can then process B times C. Okay. So that's the main problem. That's what's creating a lot of trouble when you want to do top-down processing, because you had to transform into LL1, which is creating that kind of problem. If you would be doing a bottom-up parser, this problem would not even be there, as we will see later. Because for a bottom-up parser, you don't need to have LL1. So what we need to do is to have inherited attributes. Remind you, inherited attributes is basically that the information is migrated from a sibling to another, okay? Generally from in this direction, because we're processing from left to right, of course. So that eventually what's going to happen is that the operand, the right operand of the times is going to be migrated from here to here to here, and then the left operand of the times is going to be migrated from here to here. So that then the T prime node will have the left and the right operand, and then it's going to be able to process them. Okay. Now you might ask, why is it that it's not going from here to here directly? Because we also had to do a factorization, and then eventually we see here that this is the case here. This is another more representative case of what's happening. So here we have this F here, which needs to actually be propagated here. So it actually goes from here to here to here to here. Okay. So this is where you have to be systematic into how you will do this attribute migration. Okay. So I'm going to show you how to do this systematically, what it involves to do it systematically. What are the concepts involved in doing it systematically? The problem here is that the left operands are available on a different subtree. So they have to be migrated sideways across different subtrees in order to be aggregated and processed. Now, how do you do that in a recursive-descent predictive parser? So the idea is that you're going to introduce, first of all, you want to introduce semantic records inside of your functions, because what you want to do is to aggregate information. You want to construct information. So you're going to have to create some kind of data structure. In our case, eventually, it's going to be a node. So all the semantic, all the parsing functions that are aggregating information are going to contain a node that is going to represent the top node of their own subtree. And then you're going to eventually graft nodes or children node of this tree of this node by creating them by calling other functions that are going to create these children nodes and eventually subtrees that you're going to graft into the entire tree that represents this non-terminal symbol. So for every parsing function that is making semantic aggregation or processing, you will need to have a semantic record. In our case, it's going to be a node, but here it's more, the example is more abstract by having semantic record. Okay, so this first parse function here is creating this empty semantic record. And then it's going to pass it onto this parsing function E. The assumption in this whole example is that you are passing these as, where do I say that? As reference parameter passing. Okay, it's very important to understand that. You create the node here, and then you pass it as a reference here. The effect of this is passed by reference is that E is going to create this node and fill it up with things so that actually when it comes back here, as the effect as E is actually affecting on the definition of ES, it is actually changing the state of ES here because it's passed by reference. Okay. Very important to understand that. So ES is created empty here, is passed upon E. E does some processing, fills it in with some information, and then when it returns, then ES is now been processed by E. Okay. Then you can continue the parsing. So SEMREC potentially represents any kind of semantic record. In our case, it's going to be 3 nodes eventually. In this particular example, what I'm processing is the type information. In our case, it's going to be 3 nodes. It could in fact be both. So you could have a tree that actually contains the type information. Of course, that's going to eventually what's going to happen, but only when we do the semantic checking. So in our case, for assignment number 2, the only thing you're going to do is to create a tree. It's not going to contain the types inside of the tree. Okay, so in the project, what you will eventually do is to have these actually contain abstract syntax tree or subtrees. So this function E here actually receives this semantic record from its calling function here. And as you see here, then ES is actually being instantiated or some values are being put into ES by this here. Okay. And what is this here? It's actually what's happening here is that, well, here, first of all, as you process an E, you need a synthesized attribute of a T and a synthesized attribute of an E prime. Let's go to the you process an E, you need a T and E prime S. You process an E, you actually need this synthesized attribute of the T that it gets from here. So that's a synthesized attribute of a T that flows here. And then you need also a synthesized attribute of the E prime that is represented here. So that as E is doing its processing, it needs this synthesized attribute of T and this synthesized attribute of an E prime. Then eventually, this E prime needs to actually process this plus here. So it will actually need to be passed this synthesized attribute of T into when this function is being called. So that's what's happening here. So you see that T is actually being passed this empty record. T is being passed this empty record, and it does this whole thing here. Eventually, it processes this whole thing here, and then this record gets filled by the effect of T. And then eventually, and that's where the inherited attributes is happening. You see that T is being passed the empty TS, processes this TS, basically fills up this TS, and then passes it onto E prime. So that's where the synthesized attribute is happening. Okay. So the inherited attributes is happening when you actually return. Of course, the function returns to the calling function, and it's passing this semantic record by the effect of having filled its parameter, which is received by reference. But the inherited attributes are basically passed across in the tree by creating a semantic record, being processed by one function. And once it's being filled, then it's going to pass it to the next or one of the next parsing functions down the line in the right-hand side. Okay, so inherited attributes passed by the effect of the passing by reference. Synthesized attributes are passed by reference across functions. And then the inherited attributes are passed across on the tree by passing the same variable which has been processed here and is passed here to another node. So that's actually how it's happening. So you see that you have some functions that receive one parameter and some function that receives two parameters. The functions that receive two parameters are the ones that actually require information that is actually in a sibling tree. For example, E prime is processing the plus, which requires the left operand. So E prime would thus have an inherited attribute, thus would have two parameters. As in addition to, it would have an inherited parameter that is used to pass its inherited attribute, as well as another parameter for its synthesized attribute. So by default, all the methods that are doing semantic aggregation or processing would have one parameter. If they need to communicate with their siblings, they would have two parameters. That's how you determine that. So you see that there's a lot of inspection of your rules and the concept of which right-hand side requires information from siblings. You're going to have to all inspect your grammar and figure out where you have inherited attributes so as to add a parameter. And then you also have to determine the semantic records that are necessary to have at the level of each branch in the parsing function, because each of the different branches may necessitate a different number of semantic records. As I explained later, for example, in the case of a statement, the tree is much bigger for some statements compared to another kind of statement. So different branches, depending on different branches that you may go, may necessitate different number of semantic or different kinds of semantic records. Okay, so that's about it for that. So you see that here, that's how you pass the semantic record from that you get from the sibling, and then you actually send it up. So you got the E prime S from the E prime sibling, which was processed by E prime, and then you say the semantic record that was processed by E prime is now the semantic record that I'm going to give back up to the function that called me. Okay. So that's about it for that. And you see that it's essentially doing the same notion here. So E prime receives an inherited attribute because it's processing the plus. It requires the left operand of the plus, so it needs one inherited attribute that it gets from the T. And then it needs its own reference parameter to pass its inherited, its semantic record up to its parent. Its synthesized attribute up to its parent. Then the same thing happens here. So you need semantic records be defined to accumulate information for this particular branch. Then you eventually call the functions and you pass the appropriate semantic records to them. Here you have the inherited attribute that is passed, is created by T as a synthesized attribute of the T, and it's been received onto E prime. This TS is this TS of the T here, synthesized attribute of the T, is now passed onto E prime. And then it's received as its inherited attribute. Okay, maybe I can explain that here. So that was E prime. So that's this one here. Let's take this example here. So this T here is a synthesized, so this is the synthesized attribute of the T as it gets here. So E has a synthesized attribute of the T. It passed this TS onto here, and eventually TS comes back here. But from the perspective of E prime, it's an inherited attribute. So this synthesized attribute that T got is received, and from the perspective of E prime, it's an inherited attribute from a T. That's why it's a TI and the definition of this function here. So it's received as a TI, but it's passed as the TS that was processed and received by T. Then you see here that this is a processing of a plus node, or node that involves plus. Then it actually is doing some semantic checking to see if the type of the TI is actually the same as the type of the right operand, which is the E prime 2. Okay. So if we go here, plus here, the E prime actually receives this parameter here, this inherited attribute from the T is the type of the left operand, and then needs to check if the type of this left operand, which is its TI, is the same type as the as this one here, as the type of this one here, which actually gets to it from here, which is the inherited, the synthesized attribute from the S here, from the E prime here. Okay, so that's about it for that. And then the T is similar to the E. So here you have, it receives only one parameter because it does not have inherited attributes. However, it has to enact the inheritance of attribute across from F to T prime. So it creates this FS here empty, passes it to F. F creates the information about the left operand, and then passes it on to T prime, which would then process it. T prime is processing the times operation. And the left operand of the times is processed by F, which is then passed on to T prime. Now T prime has the left operand and then can process it. You see, that's very similar to what we had in E. And of course, T prime is very similar to when we had E prime. So T prime receives, needs to have an inherited attribute because that's its left operand of the times operation it's processing. Then it's actually doing its own enacting of inheritance inherited attribute from translating the synthesized attribute of the F into an inherited attribute of F from the perspective of T prime. Much like what I explained using E prime. So this Fs here is actually processed. So that's the times example. Times example, that's exactly what I had in red here. So the times is processed by T prime. So T prime actually receives from F an inherited attribute from the F. And then it actually, and that's the left operand of the times, and then it assumes that the right operand of the times will come to it after T prime has been actually called and processed this operand through by way of the F here. Okay. So you see that it's a very well orchestrated choreography that you are organizing here. So it's very important that you do this very systematically. If you try to improvise it, that's where you do something wrong, and then it starts going wrong. And then you know, sometimes we're tempted when we debug things to just, oh, let me try this, let me try that. Well, if you can't go trial and error with that kind of thing. It has to be extremely systematic, and the way to fix the problems is to check that it's actually correctly systematic. If you try to wing it, you can only go wrong. Which is, any good programmer would tell you that, but that's what it is, and especially in this case. Then eventually we come to the F function, which is more simple, but interestingly has 3 different branches, or in this case it has 2. No, because this one does not have the 1 and the 0. Okay, so it has 2 branches. It's either F is an ID or it is a E between parentheses. So if it is an ID, then you come to this branch here. And then what you do is you match this ID, and eventually you're going to be able to get the type of this ID if you would have the symbol table. Okay. In our case, when you do the processing, we will not have the table, but it's just an example to show how you can do type checking if you would have the table. So all this to say that at the leaves of the tree, this is where you start gathering information. In our case, the only information that you will have is that this is an ID, and then you would have the lexeme of this token giving you what's the name of this variable. Eventually, from the name, you could look up in the symbol table, but that's something we'll do much later. All this to say, you come at the leaves of the tree. This is where you start gathering information that you will aggregate and pass up the tree. And then eventually, if you go on the other branch, which is E between parentheses, then eventually you will be passing this empty ES record to the E function, and then it will start all over again doing this thing that I just explained. And then it's going to create this ES here. And then this F is eventually going to pass up to its parent the entire subtree, or in this case, type of the entire expression that was between parentheses. In our case, that would be an entire subtree that you got, that F is going to pass to its calling function by having called E to generate this entire tree. Then you need to have these semantic actions that are, in this case, doing semantic checking. In this case, what it does, my sem checkup function here that I'm using in my T prime and E prime, it's basically checking whether or not the type of both of the operands are of the same type. If it is, then it returns this type, basically saying that you can only have plus and times operators on operands of the same type. If not, then that's a type error, which would then be propagated up. Of course, once you start having type error in an expression, then it's gonna, type error is gonna propagate up, and then the type error is gonna be at the top also. And then here, what you have is my get type semantic action, which is essentially, in this case, looking up into what eventually would be the symbol table. But we're not doing this in the AST generation. Eventually, what we're going to see in the following video for next week is that you're going to have semantic actions that are going to be called inside of your the parsing functions that are either going to create leaf nodes, or if they are actually F, for example, is at the bottom of the parse tree. When you get to a leaf of the parse tree, then what's going to do is going to create a leaf node of your abstract syntax tree. And then it's going to pass to its parent these nodes, and then the parent is going to graft these nodes together to create a subtree by using their own semantic action. So that's essentially the example that we were following here. And here what I'm explaining is that here you have in yellow, you have the synthesized attributes. So that's the fs is a synthesized attribute of an f. Fs is synthesized, fs is synthesized. So you see that in this example, you have actually very few synthesized attributes. If we go back to the example we saw before, this one here, all we had is only synthesized attributes, okay, because we did not transform the grammar yet to remove the ambiguities and so on. So the process of removing the ambiguities is factorizing some part of our right-hand sides and creating two different right-hand sides, and that's basically what is tearing our tree apart somehow and making it so that we have inherited attributes. And now, instead of having something very simple like this, and we have this much more complicated tree like this one here. So here, the only synthesized attribute is actually from the leaves is only here. You have other synthesized attributes that are flowing on the tree also here, but they are not from the leaves. And then also for each of the nodes themselves, then you have their own attributes. So in our case, these attributes, they will actually represent the subtree that is the representation of the parsed syntax tree. Okay. So these green ones here will all be trees eventually that we have created as part of executing one of our parsing functions. And then eventually these in red here are the migrated attributes, those ones that are flowing in the tree. The reds are flowing here, flowing here, flowing here, flowing here. The greens are the ones that are staying there in this node here, in this parsing function, waiting to be filled up. So for example, this fs is flowing from here and then filled up here. And this is actually fs is flowed onto the t prime s as an fi, as I explained before. And this t prime s is passing this t prime s onto ts. And then this ts passes onto this e prime function. This ts, who from the perspective of e prime is now a ti, or inherited attribute from a t sibling. So you see that is a very, again, as I said, it's a very well precisely orchestrated kind of ballet here that you want to implement. So you have to think very carefully of what it means actually before you start, so that if you think you're gonna being able to, as I said before, wing it, and then not think before you start, you're gonna run into a lot of trouble. Now, how do you do that with its own? So that was here explaining how you do that by using essentially the function called stack of these functions. Okay. Now, what if you want to do this do the same thing using an explicit stack that you define inside of your implementation? Okay. So here essentially describing exactly the same thing as we had, except from I was explaining how the functions are themselves, operation is using the function called stack of the runtime system that is running these functions, whereas here it's using a explicit stack. So again, repeat, exactly the same thing. There's no difference. It's just the nature of the stack that is different. So here you're actually calling the first function. You're eventually calling E. So you see here there's no parameter. The semantic records are passed through the stack. So first thing that happens, you create the semantic record, same thing as we had before. But instead of passing the semantic record onto E, you actually push it onto the stack. Then assuming that E, when it starts, it's gonna pop it from the stack. So essentially, we're doing exactly the same thing as before, except using an explicit stack. Then when you come to E, you see that the first thing E does is to pop from the stack. So you see that it needs to be very well orchestrated. If you forget, for example, in E to pop from the stack, then there's going to be some extraneous members on your stack, and it's going to go out of sync, and it's not going to work anymore. Okay. So you might think, oh, I'm going to use a stack. It seems more simple. Not more simple. It does not. It's not magically making things more simple. Okay. Some people might like to have their own stack. One advantage of this is that if you have this explicit stack, then you can actually print out what's the content of the stack. If things are going wrong and you see what's on the stack versus what you're trying to do, then you can detect where's the problem. That's one of the advantages of using an explicit stack. So you're calling E. This E needs to process an ES. So you push this ES onto the stack. First thing that E does when it starts is it retrieves this empty ES, and then will eventually process, create the fill in, if you want, information in this ES, and then will eventually at the end push this ES that it will have filled in. How does it fill it in? So for example, in this branch here, so this is the E gives E prime branch. So as we saw earlier, I'm not going to repeat all the concepts here of the operation because it's the same operation. So here it's going to call T and then E prime. So you need to have the synthesized attribute of the T and then the synthesized attribute of the E, which is going to be what you're going to put into your ES eventually that you're going to send up. Then, of course, you create these two empty records and then you push them in reverse order onto the stack so that eventually they're going to be consumed first by the T. TS is going to consume by the T. It's going to be called first. Then the E prime is going to receive this one through the stack. Again, here, what you're doing with this stack is you're essentially passing the parameters through the stack to the functions. And then the functions are returning their return value through the stack. Okay, and then that's how it goes. So I'm not going to repeat the function in here because it's exactly the same functioning as what I described before. Okay. So this E prime here is E prime requires a semantic record TI and E prime S. If you look at the previous implementation, the E prime actually received a parameter TI and a parameter E prime S. Here, when you call E prime, first you had push the E prime and the TS on the stack. So this E prime here will actually retrieve them both from the stack. Okay. Then eventually what's going to happen is that you are going to go in this branch, or of course this branch here. So this is the plus the E prime branch, and this is the epsilon branch. So you see here that if I go in this branch, I need different semantic records than if I go on this branch here. It's important to realize that every branch may need different semantic records. Okay. So here I create these semantic records and then I push them onto the stack empty. And then I'm assuming that T will get this, because of course, if I go in T, then the first thing it should do is to pop it from the stack, effectively receiving its synthesized attribute. Empty synthesized attribute that it will fill in and get from its child node or function. And eventually, T will return or push its own information onto the stack, which is then going to be retrieved by the second call of E prime as the TI here. So again, very important to realize this is the same kind of very well orchestrated ballet here that you are implementing using an explicit stack, explicitly managed stack. So it's not any different from the other. One of the advantages, as I said before, is that you will be able, as you trace, you're going to be able to, for example, print out what's the content of your stack. You're going to be able to see it and to see if the stack, for example, went out of sync or something. Some things may be missing from the stack because they were not pushed by a function, or extraneous things might be on the stack because they were not popped from the stack. And you would be able to see your stack and be able to see where the mistakes are more easily, possibly. And then, of course, the T function is very similar to the E function, so I'm not going to be repeating that here. And the T prime function, very similar to the E prime function. And then for the F function, very similar to the F function that we had for the when it was receiving and passing parameters. So here F, when you call F, so this F here is being passed, this empty F that was passed here. And then as F is being called, the first thing it does is it pops this record from the stack and then uses this information here. So remind you, this is exactly the same notion as if it would be receiving a parameter, right? Okay. And then eventually, as it does the processing, it does exactly the same thing, calls get type or calls the E function here. So all this to say here that these two methods are exactly the same method, except that this is using an explicit stack. Now, what I'm pretty sure that you saw here, what's a problem, much of the problem that is happening, or much of the difficulties that you are facing here, why it's become so intricate, is due to the appearance of the inherited attributes that are due to the fact that we have factorized our rules into different rules. And that's basically has broken our tree into more constituents, and in breaking a single subtree into sub-constituents that are not part of different subtrees. So then you need to pass information using inherited attributes. That's what made it more complicated, but there's a solution to it, and that's what I just explained. That's it for that. And then next week, the first video, I'm going to explain how you can do exactly the same thing, but using the table-driven top-down parser. And then eventually, I'm going to start explaining how you can actually generate the AST as part of using this mechanism. So that's it for this video. Thank you. Bye-bye.